It's hard to gaze at the heavens on a beautiful starry night and not wonder if we truly are alone among the endless expanse of stars that seems to fill the visible universe from end to end. Amid the stunning beauty of thousands of twinkling points of light from thousands of light years away, there has to be someone or something out there, right? Given the recent disclosures by the Trump administration concerning UAP, or unidentified aerial phenomena, we may be one step closer to the answer than we ever thought possible. But the truth of the matter is, science has been throwing huge amounts of effort into asking that all-important question: is there life elsewhere in the universe? And while the answer most certainly doesn't involve little green men, it does have some hard science behind it, and the needle is creeping ever closer to the yes side of the dial. Recently, there have been some very intriguing finds that have not only stirred up heated debates, but also some of the data has researchers quite literally trying to invent scenarios to explain causes other than life. I'm Zachary Brighton, and you're watching Terminus. And in this video, we'll look at some of the latest evidence in the search for life outside of Earth. From what is said to be an entire planet covered in a warm ocean, to the latest data from Mars, and why our small red neighbour might still be our best hope of finding life. This is planet K2 18b, a super-Earth located roughly 124 light-years away in the constellation Leo. It orbits a small red dwarf star that is much dimmer and cooler than our Sun, but what makes this planet so exciting is that it sits squarely within the habitable zone of its parent star, the orbital sweet spot, where conditions might enable liquid water to exist on the surface. Observations from the James Webb Space Telescope have confirmed the presence of methane and carbon dioxide in the planet's atmosphere, while notably missing any detection of ammonia. These findings strongly support the hypothesis that the planet could be a Haitian world, a theoretical type of exoplanet which features a hydrogen-rich atmosphere wrapped around a global, planet-wide water ocean. But the real buzz surrounding this world came in April 2025. Suddenly, this obscure exoplanet became an overnight sensation, plastered across global news headlines when a team led by Niku Madhusudan of the University of Cambridge reported a potential detection of dimethyl sulfide, or DMS. On Earth, DMS is a compound primarily created by marine phytoplankton, making its discovery a tantalising potential biosignature. As promising as this all sounds, we need to take a step back and see what the data really says. Subsequent measurements by independent teams have heavily challenged those initial claims, arguing that the DMS signal could be a mere statistical anomaly, or perhaps better explained by non-biological chemicals. Furthermore, even if the original analysis holds up, DMS is not a definitive smoking gun for life. We know of several abiotic pathways that can produce the compound, and we have even detected it on completely lifeless bodies like comets. Dr. Madhusudan himself has acknowledged that the current findings are far from conclusive, though he stands by his research while waiting for additional JWST data to clear up the noise. Until that data arrives, K2 18b remains a beautiful mystery on the edge of our reach. For thousands of years, humans stared up into the morning and evening sky and noticed a bright spark that shone brilliantly against the sunrise and sunset. Many ancient civilizations considered it to be two separate stars, though some knew it for what it truly was. Through the ages, it has had many names. To the ancient Babylonians, it was Ishtar. The Hellenistic Greeks named it Aphrodite. The Romans called it Lucifer and Vesper, the morning star and the evening star. By the 13th century, it was known as Venus. a name we still use today. And it is a planet that has been surprising us for centuries. With the Mariner 2 flyby in 1962, the first accurate temperatures for Venus were finally taken, revealing the planet to be an inhospitable and barren hell, with temperatures soaring over 450 degrees Celsius and an atmosphere of carbon dioxide and sulfuric acid that exerts the same pressure as being nearly a kilometre deep in Earth's ocean. There was no possible way that life could exist on a world like that. Or could it? But while down on the surface, temperatures and pressures are far too extreme for life as we know it, up in the thick clouds, it's a far different story. When you get high enough up in Venus's atmosphere, things start to change. In fact, at some altitudes, it can be described as downright Earth-like, if you don't mind the presence of raindrops made up of sulfuric acid, that is. And it was at these levels, some 55 kilometers up in the Venusian atmosphere, that the detection of a chemical that shouldn't be there at all was made: phosphine gas. Why is that an important chemical, you may ask? Well, for starters, we know of only two processes for making phosphine, as part of a manufacturing process and through life. Certain anaerobic bacteria produce the gas as part of their normal metabolic systems. So, we've potentially detected a gas that we know can be from a biological process. And if that wasn't exciting enough, there's more. Phosphine gas doesn't necessarily like being phosphine gas, and will react with an oxidizing environment, like Venus's atmosphere, to break down into different chemicals. That means that if there is phosphine in Venus's clouds, it has to be actively coming from someplace. And last time we looked, we didn't see any factories on Venus. And I know what you're thinking. All that sounds tantalising. But what's the catch? And you'd be right to be skeptical. The problems with this are twofold. Firstly, there has been an intense debate over the actual detection of phosphine in Venus's atmosphere. Some researchers claimed it was actually a completely different compound, or it was a mere data artifact, or that the phosphine was there but in quantities so small as to be irrelevant. However, more recent data utilizing improved techniques has redetected the gas. Still, the finding is not universally accepted, and the scientific community is anxiously awaiting definitive data from future missions. The second problem, however, might be an insurmountable hurdle for the life argument. Recent developments in the detection of active volcanism on Venus have implied that the true source of the phosphine could be active, explosive volcanoes violently belching out the gas in large quantities rather than biology. And to further dampen any hopes, the James Webb Space Telescope recently detected phosphine inside a cold brown dwarf about 54 light-years away, proving beyond a shadow of a doubt that there are indeed abiotic ways to produce large amounts of phosphine without life ever entering the equation. Even still, just the sheer possibility that life could find a foothold in the Venusian cloud decks radically expands our understanding of habitability and greatly increases the types of places we can look at next. In the 17th century, Galileo pointed a crude telescope at Jupiter and shattered our view of the cosmos. The 4 Jovian moons he discovered directly defied the geocentric model. But Galileo couldn't have known that one of those worlds might hold our best chance at finding alien life. This is Europa. It is one of Jupiter's largest satellites, surrounded by a chaotic orbital family of 115 moons. At first glance, Europa's most striking feature is what it lacks: craters. Unlike our heavily scarred moon, Europa possesses a remarkably smooth, bright face, fractured only by a chaotic web of dark, reddish ridges. This lack of impact scars means the surface is incredibly young, constantly being erased and renewed. Scientists estimate the ice sheet is only 40 to 90 million years old, a mere blink of an eye compared to the Moon's 4.5 billion year lifespan. Something dynamic is happening here, and the secret lies deep underground. Europa is caught in a brutal gravitational tug-of-war between the immense mass of Jupiter and neighbouring moons like Io and Ganymede. As Europa follows its eccentric orbit, these competing gravitational forces continuously stretch and squeeze the Moon. This process, called tidal flexing, generates intense friction and internal heat. It works just like bending a metal paperclip back and forth until it burns to the touch. This internal friction prevents Europa from freezing solid. Beneath a global crust of hard ice, tidal heating could possibly sustain a vast, liquid water ocean. If it does exist, this hidden sea is estimated to be 60 to 100 kilometers deep, with some estimates placing it as deep as 200 kilometers. That would be far more liquid water than all of Earth's oceans combined. Covered by an icy shield and warmed from below, Europa is easily one of the most promising places to look for alien life. Astute viewers will notice that I said Europa might have an ocean of liquid water. This is where things get exciting. While the overwhelming scientific consensus points to a liquid ocean, this has never been definitively proven. Competing theories actively debate its composition. Is it a chloride-rich sea similar to Earth's? Or does a sulfate-rich version exist kilometers below the granite-hard crust? So, why are scientists so confident a salty ocean exists? It comes down to three key pillars of evidence. First, Europa possesses an induced magnetic field. While the Moon cannot generate a true magnetic field on its own, it uses Jupiter's powerful magnetic grip as a boost to generate electrical currents beneath its surface. A vast, salty ocean is the perfect conductor to induce those currents. Second, Europa exhibits its own version of plate tectonics, though on a completely alien scale. The icy crust moves in massive sheets, mimicking Earth's tectonic plates. We have observed clear subduction zones and deep fault lines where these sheets collide. This constant grinding motion is almost certainly lubricated by liquid water churning directly beneath the ice. Finally, as we explored earlier, Europa undergoes immense gravitational strain. The relentless tidal flexing from Jupiter and the neighbouring Galilean moons generates massive internal friction. This constant thermal energy is the single biggest factor keeping the subsurface ocean warm and sustainable. Together, these three lines of evidence transform Europa from a frozen rock into one of the most compelling targets in the search for life. Unlike Venus, where the door to active life detection seems to have been slammed shut for now, or even planet K2 18b, where the presence of DMS remains an unproven anomaly, Europa is a world of genuine possibilities. It is so tantalising that NASA currently has a dedicated spacecraft hurtling through the void of space, on track for an April 2030 rendezvous with the icy world. The Europa Clipper is an ambitious orbiter packed with highly sensitive instruments. It is scheduled to execute 49 low-altitude flybys, gathering detailed data to paint a definitive picture of the Moon's true habitability. While Europa Clipper cannot detect living microbes directly, it will scan for molecular patterns that hint at biological activity. This will give researchers the perfect target for future missions. There are many viable paths biology could take in a place like this. Life could flourish by utilizing energy from Jupiter's immense radiation, or by clustering around a volcanic seafloor that pumps warmth and organic compounds into the salty depths. Even the icy crust itself could play a vital role. When massive sheets of ice sink below the surface, they may transport organic chemistry from the exterior down into the hidden waters below, giving life an entirely separate source of vital nutrients to draw from. When you look at all the potential ways biology could thrive, it is easy to see why astrobiologists are so eager for the Europa Clipper to come online in 2030. Europa remains one of the absolute best places in the cosmos to search for signs of life. Next, we come to a moon that some argue should be the main attraction in our search for extraterrestrial life, Enceladus. The strange thing is, if not for a quirky bit of serendipity, this tiny satellite orbiting Saturn might have remained completely obscure. In 2004, the Cassini space probe arrived in the Saturnian system to begin a multi-year study of the gas giant and its surrounding moons. In February 2005, as the probe captured its initial routine images, it photographed Enceladus backlit by the distant sun. Through sheer chance, that specific lighting geometry revealed something remarkable. Looming over the dark silhouette of the moon's south pole were giant plumes of liquid water venting directly into the vacuum of space. While scientists long suspected water existed elsewhere in the solar system, these photographs provided our first unambiguous, direct evidence of active eruptions. The discovery completely upended the scientific community overnight. NASA actually delayed the public announcement until March of 2006, executing rigorous checks to ensure Cassini's instruments hadn't experienced a glitch. But once the data was confirmed, the truth became undeniable. Enceladus was not just a frozen ball of ice, it was an active water world. Like many space missions, Cassini operated under intense pressure, with competing teams desperately vying for limited observation time. Originally, Saturn's massive moon Titan was the undisputed priority, especially since Cassini carried the Huygens lander, which successfully executed humanity's first landing in the outer solar system. But the discovery of active plumes changed everything. Enceladus instantly shifted from a mere formality to an absolute priority. The entire mission profile was overhauled to squeeze in as many close flybys of the small moon as possible. Because Cassini carried no instruments explicitly designed to analyze active geysers, the mission team had to improvise. What they achieved was nothing short of ingenious. They managed to repurpose the tools already on board, transforming several of Cassini's existing instruments into advanced chemical sniffers. Mission controllers planned a daring series of orbital passes that would dive the spacecraft directly through the active plumes erupting from the south polar region. By flying straight through the frozen spray, they allowed the venting water and ice grains to literally smash against the probe's detectors. This violent impact instantly vaporized the particles, allowing the onboard sensors to process and study the chemical composition of the hidden ocean below. What Cassini discovered while plunging through those plumes will go down as one of the most significant scientific discoveries of all time. While that sounds like a bold overstatement, it is a conviction firmly held across the planetary science community. What the data revealed was mind-blowing. Cassini confirmed that the towering jets were composed of liquid water, but more importantly, the instruments detected ample amounts of molecular hydrogen. To an astrobiologist, this specific signature is a clear indicator that Enceladus possesses active hydrothermal vents, powering rich chemical reactions deep on its ocean floor. The jets also contained complex organic molecules and the fundamental building blocks necessary for life as we know it. In other words, if you were to create a checklist of the preferred ingredients needed to forge a habitable world, Enceladus checked every single box. Yet, even with these stunning results, we must maintain a cautious perspective. Possessing the raw ingredients for biology is a monumental finding, but it does not automatically guarantee that this alien world has the ability to blend them all together into living organisms. Looking ahead, humanity is already planning a return to this enigmatic moon. Both the European Space Agency's L4 concept and NASA's proposed Orbilander are tentatively scheduled for launch between 2038 and 2042. There are even privately funded concepts being discussed, notably from the Breakthrough Foundation, the same group behind the Breakthrough Starshot solar sail project. The ultimate hope is that these purpose-built spacecraft and landers can explore Enceladus with advanced, modern technology. By analysing the active plumes and surface ice directly, these upcoming missions can finally unravel the Moon's remaining mysteries and shed definitive light on whether true alien life exists inside this tiny frozen world. For over a century, science fiction has been filled with tales of men from Mars, strange creatures from space who want nothing more than to conquer our planet. At times, these fanciful tales even received a bit of help from the scientific community. Most notably, Percival Lowell mapped out fictional Martian canals in meticulous detail. His books directly influenced authors like H.G. Wells, who went on to pen The War of the Worlds in 1897 as a dark, romanticized projection of Lowell's dying world. This fascination goes back even further. For as long as humanity has gazed at the night sky, that distinct crimson dot has dominated our collective imagination. However, any lingering hopes of finding advanced alien civilizations were soon swept aside as advanced telescopes began to paint an increasingly clear picture of the harsh Martian landscape. The ultimate reality check came in 1976, when NASA's Viking 1 probe touched down on the plains of Planitia. The historic lander confirmed our neighbour was a freezing, radiation-baked desert with no signs of active life. Yet, it did provide a massive surprise. While the surface looked completely dead, Viking's instruments revealed that the soil actually held traces of trapped water, hinting at a deeply complex past. Decades after those initial Viking missions, scientists began taking a closer look at the data. In 1987, physicist John E. Brandenburg analysed planetary maps and originated the groundbreaking hypothesis that Mars once hosted a primordial northern sea, which he dubbed the Paleo Ocean. This early model faced intense skepticism as higher resolution images were gathered in the late 1990s. Yet, rather than being tossed into the bin of disproven ideas, the model evolved as new data poured in. By 2015, advanced orbital mapping led researchers to surmise that Mars once held enough surface water to cover an area roughly the size of Earth's Arctic Ocean. On the ground, NASA's Curiosity and Perseverance rovers heavily strengthened the case for a wet Martian past, discovering concrete signs of ancient lake beds and beautifully preserved river deltas. But the most definitive evidence by far came from China's Zhurong rover, exploring the lowlands of Utopia Planitia. Utilizing specialized ground-penetrating radar, Zhurong peered tens of meters beneath the dust and detected distinct, sloping underground layers. These structures provided an unmistakable geological match to fossilized coastal beach ridges and shorelines shaped by ancient ocean waves on Earth. For decades, scientists fiercely debated whether Mars's wet past was defined by a vast, stable ocean or merely by short-lived flash floods and isolated crater lakes. But the latest radar profiles and topographic mapping have pushed the scales. By tracing ancient continental shelves and finding buried beach sediments beneath the Martian soil, we are realizing that the red planet didn't just have water, it had an ocean. In 2013, as part of its pioneering sample-gathering mission, the NASA rover, Curiosity, drilled deep into a target known as the Cumberland Mudstone, an ancient sedimentary rock nestled within the Yellowknife Bay region of Gale Crater. Initially, an experiment hunting for amino acids yielded no results. However, when researchers painstakingly reassessed the data years later, something truly remarkable was spotted. The samples actually contained the largest, most complex organic molecules ever discovered on Mars, specific long-chain alkanes known as decane, undecane, and dodecane. This is a big deal. This is a very big deal. I cannot stress to you how important of a find this was. It is highly probable that these carbon chains are the fragments of ancient fatty acids, the fundamental chemical building blocks universally used to construct cell membranes in living organisms. While chemical degradation over billions of years makes absolute certainty difficult, a groundbreaking follow-up study in early 2026 dramatically raised the stakes. By calculating how much material was destroyed by modern cosmic radiation, scientists realized the mudstone originally contained an astonishingly high concentration of these organic precursors. In fact, the sheer volume is so immense that NASA scientists confirmed known non-biological sources such as meteorite impacts or geological chemistry cannot fully explain it. While astrobiologists stop just short of declaring it an official biosignature, and the authors of the study are quick to point out that more data and further laboratory studies are needed to validate their findings, it stands as one of the most compelling whispers of past biology ever recorded. But it isn't the only one. On the other side of the planet, another robotic explorer found a clue that may be even more breathtaking. In a region of Sapphire Canyon, at an outcrop called Chayava Falls, NASA's Perseverance rover detected something truly monumental. Not only did it find complex organic carbon-based molecules, but it also uncovered distinct evidence of chemical reactions fundamentally associated with biological processes. Locked within a small core of rock, officially designated as Sample 25, were tiny black spots that were nicknamed poppy seeds, indicating organic material alongside larger, ringed leopard spots that served as clear clues of intricate chemical interactions. Utilizing its advanced Sherlock and Pixel instruments, Perseverance analyzed these rings and detected the unmistakable signatures of two specific minerals, vivianite and greigite. On Earth, these iron-rich compounds are intimately linked to microbial life. What makes this find so fascinating is the context. While non-biological pathways can technically create both minerals, those processes require intense volcanic heat, and there is absolutely no geological evidence of such conditions anywhere near this part of Jezero Crater. Instead, the presence of these minerals, sitting right alongside organic carbon and sulfur, points heavily toward a biological origin. It suggests ancient Martian microbes may have actively catalyzed these reactions, much like how sulfate-reducing bacteria form greigite in Earth's ancient sediments. While scientists must remain cautious, this stands as the single most compelling potential biosignature ever recorded on another world. The absolute strongest hint of alien life we have ever discovered. Yet, the only way to prove it for certain is to bring these pristine tubes back to a laboratory on Earth. But a frustrating barrier stands in the way. The joint Mars sample return mission is currently facing steep obstacles, with the White House proposing to cancel the current framework over soaring budget costs. If you're President Trump and you're watching this, turn to your top NASA guys and ask, why the hell aren't we getting this stuff back to Earth? And then make it happen. Because the profound benefits of an answers-in-hand mission surely outweigh the temporal costs. Until those physical samples return from worlds like Mars or the icy plumes of Enceladus, we are left to speculate based on data beamed across the void. But in the meantime, with each successive mission and each breathtaking discovery, we inch ever closer to answering the most profound question mankind has ever dared to ask. Is anyone else out there